So I must admit I confused our host by changing the title of my presentation at the last minute, as you will have noticed. Today I'm actually here to talk about the impossible mission of achieving zero-emission flight in aviation. And in particular, the role that I think all of us, whether we're in an OEM company or in the supply chain or other partners around the industry, will need to play if we're going to give that mission any chance at all. I'm going to focus a little bit on hydrogen electric propulsion. I think that the arguments for hydrogen electric propulsion are pretty compelling. But as an OEM colleague of mine told me recently, it's not the strength of your argument that matters, it's how hard you negotiate. And in the world of maintaining the status quo, there are some pretty powerful negotiators out there. Probably the most compelling argument for hydrogen electric propulsion is the fact that the current status quo really isn't very sustainable. The aviation industry today, you saw the charts just a second ago, that growth in flights means that aviation's impact on the environment today is greater than it was yesterday. And tomorrow, our impact on the environment will be greater than today. And the impact that aviation is having is greater than most people inside aviation understand, and certainly not in governments and also the general public at large. And the days where those people, those industries, impact the environment and contribute to global warming effectively free of charge and without consequence are surely not going to stay with us for very long. And this is the reason why I want to particularly focus on hydrogen electric propulsion. But before I do that, I thought it'd be useful just to level set as to how aviation is impacting the environment. And some of this will be well known to a number of you, but not to all. So today, the average large aircraft consumes something like 5,000 kilograms of fuel per hour. And that 5,000 kilograms of fuel translates into about 15,000 kilograms or 15 tons of carbon dioxide that are emitted per flight hour on an aircraft. And this year we're forecasting something like 70 million flight hours. So collectively across the whole of aviation, something over 700 million tons of carbon dioxide will be emitted. The main challenge with carbon dioxide is not the fact that we're emitting 700 million tons of carbon dioxide, because that sounds bad enough. But the issue with carbon dioxide is that carbon dioxide stays in the atmosphere for hundreds of years. So we're not just worrying about the 700 million tons of carbon dioxide emissions this year, or maybe the 750 million tons of carbon dioxide emitted next year. But we're also worried about the cumulative effect of all of that carbon emissions over many decades. And in fact, with carbon dioxide staying in the atmosphere for hundreds of years, that means literally every single aircraft that has ever flown, we are still suffering from the consequences of those emissions. So it's actually the cumulative effect of carbon dioxide, which means that the emissions that we create this year are going to stay with us, contributing to global warming for many decades to come. However, carbon dioxide is not the only way in which aviation is impacting the environment. So this is, so if we take carbon dioxide as the starting point, the other key contributor that we have is nitrogen oxide. Now, nitrogen oxide is created in the combustion engine when we take air, which is sort of 78% nitrogen, combust the fuel. We end up with nitrogen oxides in much smaller amounts than carbon dioxide, but nitrogen oxides are much more powerful as a greenhouse gas, about 300 times more powerful. And in addition to that, they also have negative effects on people's health and ecosystems and so on. So nitrogen oxide is not that far behind carbon dioxide in the overall sort of negative implications of aviation on the environment. And then the third, but potentially the largest contributor that we have as an industry is actually the contrails. So contrails are formed when particles from the exhaust stimulate air crystal formation in flight, and those contrails form effectively pseudo-clouds. Many estimates believe that contrails contribute something between 30 to 50% of aviation's impact on the environment. Now, there's an awful lot of, this is a really hot topic right now. In particular, here in Germany, with some great work led by the DLR, there's an increasing understanding and knowledge of contrails, and I'm not going to spend a lot of time on that. All I would say to those who are involved in contrails is, unlike nitrogen oxides and carbon dioxide, these are things we can do something about now. Contrails only have an effect between sort of 10 and 15 hours maximum. So here, we have the opportunity to make a significant reduction in aviation's impact. My only message to those people involved is it's all about pace and decisiveness to get this done. Coming back to carbon dioxide. Now, carbon dioxide is generated in different ways for different ranges of flight. Most of aviation's flights are actually relatively short. So 80% of flights are below 2,000 nautical miles, and those 80% of flights only generate about 40% of aviation's carbon dioxide emissions. Conversely, the top 10% of longest flights contribute 50% of aviation's impact on carbon dioxide. So the key message here is length matters. If we're going to really impact and reduce aviation's impact on the environment, we're going to have to push the range capability at which we can eradicate emissions. And there are several different ways in which we can do this. Battery electric is a fantastic technology, definitely zero emission. However, the range potential, even for the next few decades, is still relatively limited. And as you can see on the very left-hand corner of the screen, the opportunity for that to have an impact globally on aviation's carbon dioxide emissions is relatively small. There is the opportunity to use gaseous hydrogen, and I'll come to hydrogen in a second. However, with gaseous hydrogen, the increase in weight associated with the pressurized tanks offsets the benefit, and the range capability is probably fairly limited still. And that's the reason why pretty much everyone in aviation is talking about liquid hydrogen. And with fuel cells, liquid hydrogen has the ability to push that range capability further. The challenge we get then is, as you start to increase the range capability and the payload capability of aircraft, the power requirement gets much bigger. And as that power requirement gets bigger on an electric aircraft, with conventional technology, that ultimately means pushing voltage up. And voltage at altitude is much more challenging than voltage on the ground to manage. And that's the reason why GKN Aerospace are focusing on a technology which I'll come to in a second, which is all about enabling much higher power, but without increasing overall voltage levels. We don't know what the limit of that capability is. However, we do also believe that at whatever point that limit of capability comes, hydrogen combustion is also a potential technology which has the opportunity to expand that payload range for the entire requirements of aviation. So, a bit of basic level setting in terms of hydrogen. Really important stuff because it fundamentally drives why all of this is quite complex. So, hydrogen, a single litre of kerosene gives us about the same level of energy as about 1,000 litres of hydrogen. Now, clearly, we're not going to carry around 1,000 litres of uncompressed gas, so if you compress that, you can get that down to about, let's say, 6 litres of hydrogen. The alternative, which is the reason, and by the way, that's extremely high pressure, very, very heavy tanks, which means the weight is clearly an issue. The alternative is therefore, as I've already said, moving to liquid hydrogen. And liquid hydrogen, you can get that down to about 4 litres. So just take a second. That means to get 1 litre of energy, the same amount of energy as a litre of kerosene, you need 4 litres of liquid hydrogen. Now that 4 litres of liquid hydrogen is actually a third of the weight. So on one hand, you've got a really great environmental solution because there is no carbon in the fuel. So you've got a really low weight, really great environmental solution. offset by the complexities associated with storing a liquid at minus 253 degrees on an aircraft, and all of the complexities of managing that, and clearly cost and so on. So we have to balance those in any design we come to. And ultimately, that drives a significant change in the architecture of at least the systems, if not the aircraft themselves. So where does a company like GKN Aerospace even start on this type of mission? Because GKN Aerospace are not an aircraft OEM. We have some legacy. The Fokker company is part of GKN Aerospace. And we also have an engines business with legacy in Sweden with OEM capability. But we're not an OEM. We don't have a strategy to be an OEM. Where do we start? Well, the reality is we sort of had to start from the beginning. We weren't in a position where our customers were giving us the technical requirements for a hydrogen electric propulsion system. We weren't in a position where we could go to the regulators and say, how will these regulations change with the introduction of hydrogen electric? We weren't in a position to go and talk to our supply chain and buy the individual components of a system that we could then integrate into an aircraft, let alone being able to understand what the requirements for that type of system were for an aircraft that doesn't exist, that our customers haven't even decided themselves what that will look like. So we effectively had to operate like a pseudo OEM. We had to operate, as I call it, one level above our station to anticipate what those future requirements of those future aircraft, of those future technologies might be. And the way that we did that is we developed what we call our notional aircraft concepts. And these notional aircraft concepts are not just pretty DMU pictures. These are concepts that have been analyzed for aerodynamic performance, handling performance, takeoff landing performance, aerodynamic loading, structural sizing, and how all of those drive the optimization of the systems themselves. And we've done that in order to then translate those needs into the requirements for the technology on our aircraft. And how does that work? Well, it takes cold, low-pressure air from outside the aircraft. We then have to compress that air, which then increases its temperature. We then have to cool that air, so we give air of the right pressure and the right temperature to our fuel cells. We then have hydrogen that's stored as a liquid, as I mentioned, on the aircraft, which we then need to increase the temperature of that liquid hydrogen to a level that we can then transition to a gas and pass it into the fuel cells. The fuel cells then create an electrochemical reaction. So, and the byproduct of that air and hydrogen creates an excess of heat and water, and that heat needs to be managed through a combination of ram air and also some other cooling medium. Now, the really clever part of our system is that the electrical power that's generated, we mentioned the fact that we have to heat up the hydrogen. We do that as a byproduct. We manage to cool down helium as a separate medium. And that helium is used to cool our electrical network and our electric motor. Why is all of that important? What that does, by reducing the temperature of the network, is we significantly reduce the resistance of the power distribution and also the electric motors. And by doing so, we improve drastically the efficiency that is possible. And all of that efficiency cascades back upstream into the sizing of the fuel cell system and level of power and fuel needed on the aircraft. We've only just started over the last 3 years on our journey. And H2 Gear was our first big program, started in 2020, which is all about the power system on the aircraft. So far, we've managed to complete almost the full detailed design of our ground-based demonstration components. And at the beginning of next year, we're going to start the physical test of those components. Moving into the following year, we then integrate those into a ground-based demonstration, which we aim to finish by the end of 2025. At the same time, we're also now launching with our partners, Parker and Marshall, we're starting another program, which is then to do the same process on our fuel cell system. And then subsequently, and yet to be announced, we will be taking both those systems to a flight demonstration by the end of 2028 with a particularly well-known Brazilian regional aircraft company. Our ambition is to enable the maximum possible range to be achieved for zero-emission flight. And already, just in the last 3 years, we've created a huge amount of innovation with 131 inventions raised, 20 patents filed already, and a further 11 that are currently being drafted. Now, it's probably fair to say, even just at the level that I described, which was pretty much the sort of 35,000 feet level of description of our system, you can probably already start to get a feel for the fact that this is actually pretty complex stuff. And probably the biggest challenge for us is that no matter how good a job we do at developing this technology, even if we absolutely blow it out of the park, even if we deliver the best possible concept, we can't be successful unless our partners, our suppliers, our customers are also on the journey with us. The reality is this is all pretty complex and difficult stuff. And even if the products work brilliantly, they cannot be successful unless there is a vast amount of liquid hydrogen that's available, that's been produced using renewable electricity in order for it to be properly green. It can't be possible unless the right economic conditions are set through the right policies that are globally collaborated on. And our customers, ultimately, they're the ones who have got the really big, bold decisions to make. The decision to launch a brand new aircraft that bases itself on a fundamentally different technology. Wow, that is a bold decision by any OEM. And that OEM needs the confidence of their customers that not only will the aircraft operate how they need it to operate, but all of that other complex stuff, the infrastructure around the airports, the availability of hydrogen, the economic policy decisions, all of those things need to convince the OEM's end customers to put their money on the table and say, yes, we want to invest in the future. Now, the challenge for all of us is if we wait for the customer to launch that product, it will be too late. If we wait for hydrogen to be available at destination at the airports before we decide to invest, it will be too late. If we decide to wait until the governments have enforced policies which push aviation into a direction of zero emission, it will be too late. Ultimately, all of us in this room need to operate one level above our station if we want to be successful. We need to anticipate the future needs of the aviation industry. We need to invest, and we need to convince our owners, our boards, our people that this is the direction that is going to make aviation sustainable for the long term. Ultimately, the route to zero-emission flight is only possible if we all believe that it's possible. And every day that we make the efforts to make that dream a reality, the less impossible it will become. Thank you.